Hey everyone, today we're going to be talking about graphing transformations. Before we get started, it's good to start off with these 5 very quintessential functions. The graphs that they represent are commonly known as parent graphs. The word parent graph is supposed to be indicative of a sort of starting point, so to speak, because in a college algebra class or a pre-calculus class, when you're talking about graphing transformations, you're generally starting with one of these 5 functions and you are translating it or moving it or flipping it around the xy plane to get the desired transformation. So it'll be important to be able to look at one of these 5 functions and understand the shape that it's going to make. The idea with a graph transformation is you'll be able to start with one of these 5 functions and then manipulate it somehow to get the actual transformations that you want. Let's go ahead and talk about what these actual transformations will look like. Suppose that we're starting with a function f of x. One thing that we can do is we can move the function to the right by a units in the xy plane. The way to do that is to alter the input of f and evaluate f of x minus a. To move a function to the left by a units, you would alter the input this way by computing f of x plus a. To move a function up by a units in the xy plane, you wouldn't alter the input, but you would alter the output. So to move a function up, you compute f of x quantity plus a. To move a function downward by a units, you would compute f of x minus a by altering the output, not the input. So to recap, to move a function left or right, you're altering the input of the function, and to move a function up or down, you're altering the output of the function. Something else we can do is flip the function vertically on the plane by computing negative f of x. Lastly, we can flip the function horizontally by computing f of negative x. So to summarize, the kind of transformations we've talked about here are shifts and flips. Notice that in this first column, all of these shifts and flips have to do with the x-axis, where the vertical flip would be called a reflection about the x-axis. Likewise, everything in my right column has to do with a shift or flip about the y-axis. Let's look at some examples. Take the function f of x equals to the absolute value of x and perform the following transformations: a reflection about the x-axis and a shift of 2 units to the right. To answer this, we'll deliver the drawing of what this should look like, and we'll give the actual function after the transformations have taken place. Based on the parent graphs in our first slide, we know what the absolute value of x looks like. We have this graph that looks kind of like a V. So to perform our first step of a reflection about the x-axis, it looks like a vertical flip, which is demonstrated by the graph in the middle. In describing the actual function that we get after this transformation, we end up with negative absolute value of x, because with a reflection about the x-axis, we multiply the entire function by -1. Now, moving on to step 2, we need to move our function 2 units to the right. Graphically, we have our upside down function shifted 2 units to the right, and since this is a shift along the x-axis, we have to alter the input of this function. So by definition, that would look like f of x minus 2, so in our case, that would look like negative absolute value of the quantity x minus 2. And that's all we need to do. We've carried out both steps of the transformation, and we're done. We have a picture and a function. This is why understanding the parent graph is so crucial here, because since we knew what the starting graph looked like, we know what the transformation will look like at the very end, because we can visually just draw the graph based on the transformations we're given, and then we can manipulate our function by the algebraic steps described in the previous slide. So if ever you're given a parent graph and told to transform it, you just follow the steps on the previous slide, draw the picture if you need, and you'll end up with a process that's very similar to what we just did. Now let's work backwards. Let f of x equal x squared, and let g of x equal minus x plus 2 squared plus 1, and we will describe the transformations that took place starting at f of x that land us at g of x. With problems like these, it's best to locate the variable x and sort of work our way from the inside out. Upon observation, the immediate number next to x is a positive 2. This is indicative of a shift 2 units to the left. As we work our way outside more, I notice that I have a negative sign in front of the squared quantity. That indicates a vertical reflection, or a reflection about the x-axis. Then lastly, I have this addition of 1, which indicates a shift 1 unit up. Usually when I have these kind of problems, I like to look at it and think about what's going on before I start writing stuff down. Again, the process of looking for a variable x and working our way inside out is usually the most efficient way, because every time you see an addition or subtraction, a multiplication of -1, or another addition or subtraction, that's the best way to track if your input of the function is being changed or if your output is being changed. But since I've sort of planned ahead here, I can go ahead and start writing all this down. I have this x plus 2, which is an indication of a left shift by 2 units. I have my multiplication of -1, which is indicative of a reflection about the x-axis, or rather a vertical shift. And then I have an addition of 1, which indicates a shift up by 1 unit. So those 3 bullet points would be my answer. I've described all the transformations that took place. And just for a visual guide, I have my parent graph f of x equals x squared at the top, and my transformation graph g of x equals to -x plus 2 squared plus 1 at the bottom. In this final set of examples, I'll give you a few functions to look at that have gone through transformations, and the goal is to identify the parent graph and the transformations that took place. The first function on this list includes absolute value bars, so it's easy to think that the parent graph is the absolute value of x. That is correct. Absolute value of x would be our parent graph, where the transformations that took place would be a right shift by 2 and an up shift by +6. The next function has our variable x eventually raised to a power of 3, so we can surmise that x to the third is our parent graph, and the transformations that took place here are a left shift by 3, a vertical flip, and a downshift by 2. Our next function involves a square root, so the square root of x will be our parent graph, and we'll have a left shift of 3, a vertical flip, and an up shift by 2. In the last function we see a quantity squared, so x squared will be our parent graph with a left shift of 2 and an up shift by 3.